All right, okay. Finally, we'll get started. Sorry. I don't remember the code to get in. Also, yeah, there's been some confusion with the examples for homework 3. Sorry, so what had happened is the TAs fixed it, I forgot to upload it, and there was a lot of back and forth. Go and get the latest versions that are online. And there should also be the jar file. So you can actually run our version of the code, and you can see the output. You can also see what's on the console. It actually shows the board after every single move, and usually gives an explanation if the move is not valid. So hopefully that will be useful. Any questions about the assignment or anything? No? Yes?
It was mentioned that there would be a script that we could run.
Yes.
When will that be posted?
Today, yeah. I will put up a script. It's sort of just a test script to check whether, I mean, it doesn't do any checking, but it just sort of checks all the names and it doesn't actually verify anything in your code. But you should make sure that it runs on your files, because that basically is what we're going to do as well. Next week is the midterm. So on Thursday, I'll do a review. As I said, I mean, go through the questions that I ask in class. Also, look at the exercises in the book. We've covered. I mean, if you go to the course website, you'll see all the chapters we've covered. Have a look at the questions at the end of the chapter. So those will be helpful. I will not be here during the midterm, so for what it's worth. All right, so we are going to do queues as opposed to stacks. So a queue is like the opposite of a stack. So remember, in a stack, you think of this as the top. You insert at the top, and you delete at the top. So it's insert and delete at the top. A queue is like what a real queue should be, where you insert at the back and you delete from the front. So let's say this is your queue, and say this is the front, and this is the back. Suppose I should have written it the other way around, but anyway. So inserts are here. And the delete is from here. Make sense? So you insert at the back and you delete at the front. So this is called FIFO, first in, first out. A stack is called LIFO, last in, first out. So just as in a stack, the terminology for an insert, you call it a push, and a delete is called a pop. In a queue, it's called NQ. That's what an insert is called, and a delete is called a DQ. So you would get a queue like this, where you could say NQ 7, NQ 42, NQ 5, NQ 57, and then I would do DQ, just to make sure that you're all awake. I want you to tell me what the Q is going to look like when I finish. Again, I'll put front is to the right and back is to the left. So is it going to be this, if I did that? Is it going to be that? Or is it going to be this? Right? So I ran these operations here, NQ7, NQ42, NQ5, NQ57, and then I did a DQ. Which of these remains? What remains? Good. At least those of you who have Post-its in their hands are awake. It's this, because this is where it starts. 57 goes at that end, 7 comes off, and you end up with that. So a nice example of what you can do with a queue, although it's kind of a really trivial example, but it's useful to look at. Detecting if a string is a palindrome. So a palindrome is a string where, okay, so let's just say you ignore spaces. So palindrome is a string where, you know, if you reverse it, you get the same string. So kayak is an example. What is it? Able was I, or I saw Elba is an example. Even the spaces work out here, right? Yeah. You've not heard of that one. Supposedly what Napoleon said when he was jailed. Most of you don't know your history, right? That's why you don't get it. All right. Go and take a history lesson. Anyway, so detecting if a string is a palindrome. Again, you know, there are easy ways of doing this. What's the simplest way of doing it? How would you detect if a string is a palindrome? Yeah?
Reverse the string compared to the original.
Just reverse the string compared to the original. You can reverse using a for loop. What you could also do is, so you could imagine, suppose you didn't know the length of the string. All you could do was run a for loop through it. Or let's say you were getting a string through a stream. You could insert all the characters into a queue. You could insert all the characters into a stack. And then what? So insert all of these things into a queue, insert all of it into a stack. Yes? Compare the stack and the queue, right? Do pops from the stack and do DQs from the stack and just make sure they're the same. Right? So that's just, I mean, I don't like that example. It's kind of stupid, but you know, it is what it is. So you could say for each character C in the string, so maybe first you create a stack, which I'll call S, a queue, which I'll call Q. Oops. So I would just do S dot push C, Q dot NQ C. And so if you see what's going to happen at the end of this process, So this is, let's say, S, and that is Q. That is Q. So if you look at, this is the top, and this is the front. So sort of badly chosen on my part for the string, but you would basically see that in this direction, you would have the string, and in this direction, you have the reverse of the string. Right, and here you have just the string itself. So when you insert into a queue, it's just like inserting into a list, right, in sort of the natural way you would look at things. And so then you can just compare these two things. Does this make sense? Yeah, nothing fancy here. So at least from a pedagogical perspective, unlike stacks where there are lots of really nice algorithms to show, for queues there aren't these nice algorithms to show, like parentheses matching or postfix notation. On the other hand, queues are used very heavily in systems where, especially if you have an operating system where you have processes coming in and there's a scheduler that has to decide which processor, which process basically gets CPU time, then you use a queue because the first one that comes in has to be processed the first. Right? So it's quite common. And eventually when you do things like breadth first search, you'll see queues again. What I'd like to go through are just how you'd implement a queue. And we'll go through the array-based implementation and sort of a linked list-based implementation. So let's start with the linked list implementation. Actually, I should probably add something to this. So I said you have NQ and DQ, and often you will also have an operation called peek. So peek is just look at the element at the front of the queue. Now stack also had a peek function, although I argue that you don't really need it. It's enough to just have a push and a pop. Is that the same for queues? Why? Yes?
Because if you take something off the top, then you would insert it back to the beginning.
Exactly. So when you do a DQ, you cannot put it back at sort of where you deleted it from. So the peek is useful. So peek cannot be implemented from DQ and NQ. This is for queues. But in a stack, a peek can be implemented from a pop and a push. In general, this is a useful exercise to compare. Yes? Yes, you could. Yeah, you could. Maybe.
It's kind of inefficient to pop and then push to do a peek for a stack.
Okay.
It's very inefficient to do that with a queue.
With a stack, it's okay. You just do a pop and a push, and that's fine. With a queue, yes, you could do it by removing it, then sort of putting it. You can essentially DQ, NQ, and do that over all the elements to get things back. You can. So efficiently, yes. So that's a good question. So what you're asking now is actually how do you implement a queue, right? And it depends on your implementation. So naturally, you'd like an implementation where you're not sort of moving things around all the time. which is why it's natural to start with an implementation of queues using a linked list and sort of see how we can get the NQ and DQ function. So remember, we saw that you can implement a stack using a linked list, and it's fairly efficiently. You can also implement a queue using a linked list, but there's a slight twist. Okay, so let's implement a queue using linked lists. Okay, so let's take our linked list, and so this is null. There's that pointing. Here's head, 42, 101, 7, and 15. So let's think about this. First, we have to choose where the front and the back of the queue are going to be, and that would affect the insert and the delete. So let's just say, okay, so sorry, I'm going to change this. It's just going to be more convenient. Let's just put the front of the queue here and the back over here. And let's say this was our queue. Right, so this is the queue that we have, and maybe this is how we've stored that queue as a linked list. So you delete from the front and you insert at the back. How would you do this? So how do you do a DQ? What is a DQ operation? Yeah? Right, so you basically, a DQ is just to delete head, which was actually the same thing as we did in a stack, if you think about it. So how do you do an NQ operation? Yeah? A tail, you mean pointer or reference? So you want to actually add your element over here. Right? So if you did something like NQ99, what you want is the following to happen. And this starts pointing here. That's what you want. Right? Do you need a tail pointer? You don't necessarily need it. If you didn't care about efficiency, you could keep going through the linked list and then finally add at the end. But you're right that to make it efficient, it helps to have a tail pointer. Right? So you would basically have a pointer called tail, which would point to the last element. And whenever you want to insert, you insert at the end, at the tail. Make sense? So there is no shifting around of all this stuff when you implement things as a linked list. Does that make sense? You don't actually have to move stuff around. So maybe I'll just write this down. So if you had a class Q, you might just implement that by having some linked list L, and in the linked list, so maybe you just have a linked list here, and you could write your DQ function would basically just delete. Well, let me actually write this out differently. So what you would have is you could have a, I'll say a node called head and a node called tail. The dequeue operation will just delete the head. The enqueue, maybe it gets a node n, will do what? So let me give you the options. Are you going to say that n dot next equals tail? Will you say tail is equal to n dot next? Or will you say tail dot next equals n? This isn't actually entirely correct. There's something more you have to do. But one of these, you need to do one of these. One of these needs to be done, right? So this is your linked list here. You want to insert something at the tail. This is an example of a question that I could ask at the midterm. How would you insert? Would you do n dot next equals tail? You have to insert a new node n. Tail is equal to n dot next, or tail dot next is equal to n. So how many of you are not sure? Raise your hand. Okay. So maybe let's draw the linked list here. I'll just draw a smaller linked list. So you have that. This is head, 42, 7, 9. And let's just say you did an NQ n, where now n is this node with 50 here. And so tail was pointing here. Is it clear now what's going to happen? You want the linked list to now be 42, 7, 9, and 50. So you want this pointer here to now point to that. And this pointer is tail dot next. So you set tail dot next is equal to n, and this will then point to this. Why are we not done? Yeah, in the back. You have to set n equals tail. Almost, yes? You have to set tail equals n. Right? So you have to reset the tail, and so then you would set the tail equals n. And so the tail moves out from here and goes there. Right? So that's how you would implement a queue using a linked list. Questions? Yes? So when we pushed into a stack, we pushed at the head. Right? So the NQ is different, but the pop and the DQ are the same. But you could actually switch those around. It doesn't matter. Yes? Stacks have heads, yeah, that's probably how most people would put it. Yeah, stacks, yeah, you'll usually refer to it as a head. Note that for a stack, you don't need a tail pointer. For a queue, you need a tail pointer. Or it's helpful to have a tail pointer. Yeah? And so just to sort of write this out, in a stack, A push is insert at the head. A pop is delete head. And in a queue, an NQ is insert at tail, and a DQ is delete head. Why didn't I do a queue the other way around? Right? So can I do this? Can I do NQ, insert at head, and a DQ is delete tail? Can I do this? I mean, it would have the same effect, right? Because it's just the Q is going to be the other way around, but I insert at the head and I delete at the tail. What's the problem? Think about it. Somebody has their hands going all the way like this. I like that. I guess that means maybe you get it. You have a question or you have the answer? Wait. If you figured it out, good. But if you haven't, I want you to think about it. Because there are reasons for making these choices. Not just that that's the way it's written in the book, which is actually one of the problems with reading a book. You don't get to see all the wrong ways of doing it. So how many of you think that is possible, if you're not sure? Okay. That's it? And how many of you don't have any idea whether it's possible or not? Some of you. And how many of you think that it's not possible? Some of you. Good. So it's like sort of even split between all three. So remember, it seems like if I just inserted at the head and deleted at the tail, I'd have exactly the same effect. Maybe I'll show you this example. I could insert at the head and delete at the tail. What's the problem? There's a problem with that. Yes?
This is a single linked list. You need a doubly linked list to have a previous function so that the node in front of the tail will be set to a null when you delete the tail.
When you want to delete the tail, what do you have to do? You have to set that pointer to null. But if you only have access to the head and tail, you don't know what that pointer is. You don't have a reference to that node. So you could use a doubly linked list, but then that's going to make your code complicated. Or you could store another thing called previous. So you store the... Yes? Yes, you can. You can always go through the list, but that's inefficient. Yes, you can. I mean, you could also copy everything into an array, do everything in the array, and then move it back to the list. But we wouldn't want to do that. If you did that in your homework, I will be very angry. Yeah. Yes? So a doubly linked list is one where there are pointers that go backwards as well. So every node has a forward pointer and a backward pointer. That's a doubly linked list. So you need to know what this is. So knowing the tail actually doesn't help you. You actually have to have a pointer to previous. And so that's why it's better to sort of insert at the tail and delete the head. You can actually always maintain a previous pointer and still make this work, but it's a pain. You'll have all kinds of null pointer exceptions the first time you code it up. And just for completeness, there's also something that's called, this is kind of weird, okay, so this is called, they call it a deck. So a deck is a combination of a stack and a queue. You can do a push and a pop as well as an NQ and a DQ. And it's a stack plus a queue. They're not very common, but Python and Java will give you access to decks if you need them. Very rarely do they actually come up in practice. Yeah? So you should just, instead of thinking of where it is with respect to the head or the tail, just think whether it's like, FIFO or not. So a queue has to be FIFO, first in, first out. So whatever was the first thing to be inserted, so you insert at the tail. So when you insert something, it's at the tail. So unless it becomes the head, you will never DQ it. So it's only the ordering that matters, which is why both of these are in some sense equivalent. If you implement this or this, it's the same. It has the same effect. Yes?
For a deck, what's the naming convention for the push or NQ function? Which do you use? Because they're the same, right?
It might be, that's a good question. I think they usually use NQ, I think. Yeah. I think when it's a deck, then you just think of you have two ends. You can insert or delete at either end. Yeah?
You said decks are rarely used in practice, and I was wondering why. Because by the looks of it, if you have a stack with a queue, that gives you, more flexibility per se. So.
More flexibility is a bad thing when you write code, in general.
Is it just inefficient?
It's not inefficient. It's just that when you only need a stack, you should only be using a stack. Because the more flexibility you have, the more chance there are for bugs and errors. Like, for example, in the parentheses case, you never need to NQ or DQ. So you don't want someone who writes code for that ends up using an NQ or DQ to screw up with the algorithm. Which is, yeah. Yes?
Does Java have its own stack and queue classes?
I believe so, yes.
Are they built over linked lists?
I'm not sure, actually. I don't know. It might actually be something like if it realizes that the things are small enough, then it'll just use arrays, because it's a lot easier to allocate memory for arrays. So that will sort of be the next thing that I want to talk about, which is if you have a maximum size on the queue, then you can actually implement it really nicely using arrays. But any questions about this? Yes?
What's a usage case for a deck?
There are like some fancy algorithms on graphs where sometimes you use a deck. It's convenient to have a deck, but there's no nice, like, simple thing where I could give you. One thing you could imagine is you may want to have a list of numbers where you want to maintain a list of, let's say, sorted numbers, where you want to actually access either the minimum or the maximum. In that case, a deck would be convenient because you have access to both ends. Yeah? You could use a deck to program a card game. Yes, you could. Yeah. I mean, you can come up with. You can cook up use cases if you're creative enough. But in general, it's probably not that useful. I mean, for example, stacks appear so commonly in recursion. And queues appear a lot in what I'll talk about, something called priority queues, where again, you have a bunch of objects and you want to sort of get the one with the minimum priority or the maximum priority. Decks are sort of, not that natural. Okay, but here's sort of an interesting thing, which is implementing a queue using arrays. It's actually kind of interesting. So you might actually have a queue as just an array. So you allocate an array, and let's just say that we know the size of the array is max. Right? So this is an array of size max. And so we could say 42, 101, 7, 15. So, so where should we put the front? Where should we put the back? I haven't even told you what the order of this thing, but just think about it. So where, if you had to code this up, where should the front be and where should the back be in the array? Yeah? Sorry, say that again? It does. I mean, so let's, okay, so maybe this is a little ambiguous. Suppose the array is empty. The queue is empty right now. So when you do NQ42, it's probably going to go there. Now when you do NQ101, you could decide to put it before 42 or after 42. Seems convenient to put it after that, right? So if you maintain, let's say, a point, let's say you maintain an index that let me call, this is the back, or maybe, sorry, this is the back. Then what I could do is an NQ operation, so the NQ sum int I would say, so let's just say, let me just call this capital Q. I could do Q of, back is equal to back plus 1, and Q of back is equal to I. Make sense? So I shift back, and then I copy the ith element. Is this clear? This is how you NQ, right? So if I NQ something over here, I put it there and I move back. How should I DQ? It's worth thinking about for a moment. Yes? So I could delete the first element and move everything back. Like, make sense? I could DQ DQ has to remove 42, and then it would shift everything back. Yes? Shifted, well, okay, sorry, I meant so, okay, maybe I should, you would delete 42 by removing this, and take all of this and move it one step in that direction, to the left. Why is that a bad idea? Yeah? It's inefficient. It works, but you have to move everything back. There's a simple, quick sort of solution that's more efficient. Yes? Well, setting every element to the equal in front of it is, again, you're basically shifting the array. You're shifting everything by one step. I claim that you don't have to shift. Yes? Shift the head pointer. Almost, but there are no pointers here. It's an array. Yeah? Like you store back, you could just store an index called front. Yes? Well, let's say you're in Java, so you don't want to do that. Yeah. That would, in general, be a bad idea, because then, yeah, you could do that, though. Yeah. Yes? Wait until the array gets filled, but, I mean, no, but when you DQ, so when you do DQ once, this should return 42. You do DQ again, it needs to return 101. Well, essentially what he said, you could basically maintain a pointer called front or an index called front, and a dequeue operation simply increments front. So let me write that down. So let's say this is front. So dequeue would simply be front is equal to front plus 1 and return q of front minus 1. Right? That makes sense? You simply return the element and then you just move the pointer. You just move the index. Someone had a question. Yes?
Won't you eventually run out of memory doing this?
Good point. So we'll get there. But first, convince yourself that this works. Right? Any questions? This make sense? Yes, no? Yes? Do you still have access to that first integer? Interestingly, you do have access, although you don't need to access it. I mean, because you have it stored in the array, you do have access until you rewrite it. But the point is, if you just implement these functions and you made everything else private, then no other process can access other elements. Right? So that would give you your data protection. So the point is, but NQ and DQ then become really easy in arrays. It's just moving an index. Yes?
When my front index is at the very end of the array, it's going to give me a array index out of bounds exception if I try to DQ.
Yeah. So I haven't handled exceptions here, but let me tell you the solution to the other problem, and then we'll see how to handle that. Yes? Does it get deleted? So not really.
Yeah, because like
You're just moving the index. It doesn't get deleted. But who cares? Right? I mean, all you want is when you do DQ the first time, you should get 42. The next time, you should get 101. The next time, you should get 7. And by moving the index, you attain that. You get what you want. Does everyone see what's going on here? This is much simpler than the linked list. I have a suspicion that probably Java is implementing this under the hood if they have some sort of bound on how large your queue is going to be. So what is the problem with this? Yeah? Well, let's just say that you know that you're never going to NQ more than max elements. Suppose you knew that you're never going to NQ more than 1 million elements. So you have an array of size million. You still have a problem. Yes? Does everyone see that? Right? If you just do NQ, DQ, NQ, DQ, NQ, DQ, it's just going to keep shifting, even though your queue only has size 1. Right? So just give you an example. So let's just do something like NQ1 DQ, NQ1 DQ. Again, NQ1, maybe I'll do 2 and 3. DQ, and I keep doing this. Note that my queue never has more than 1 element in it. But in the first iteration, this is 1, and front and back will basically be the same. Or no, I guess, where's front? So this would be front, and this would be back. And then when I do the NQ, DQ, and then I do NQ2, you're going to end up with 2 over there. And when I do the next one, you're going to end up with 3 over there, with front pointing here and back pointing there. front, and back. Because if you observe my code, it only increments the indices, never decreases them. So Q has size 1, but it's going to keep moving in this direction until finally you end up at the end, and then you get some sort of array out of bounds exception. Yeah?
So every time before you use the first and the back function, you could mod it by the size of the array, and the remainder can be the index to of that.
Very good. What you basically do is wrap around. What you do is you say, well, if you do an NQ and DQ here, you go back to the beginning of the array. Or another way of thinking of it is you think of your array as circular. Right? So it starts with 0, 1, 2, all the way up to max. Think of your array as actually circular. Yes? So you're right. I mean, you do have a problem that you might use up the entire array. So let's assume that you have some bound on the number of elements you put in the array. So let's just assume you never add, or rather assume Q never has more than max elements, which is a reasonable assumption. I mean, you might say, well, you initially allocate some memory, and then if it actually runs out, then you might copy it and blow it up or something. Admittedly, I mean, you could use a linked list to avoid all of that. But this is also a common solution when you have a bound on the size. Someone had their hand up here and there. Yes? Why isn't front and back both 1? I'm sorry, you're right. Front and back should be just the same. My apologies. Right, they're the same. Yeah. Okay, so does this make sense? So you could imagine your array to be circular. Of course, it's not circular in practice, but you just wrap it around. So if you have to NQ and DQ here, you kind of move everything back to the front. Does that make sense? So think of an array as circular, and your Q is going to be something like this. Right? So you have front over here and back over here. And so you insert over here and you delete from there, and you just kind of keep doing that. So now you don't have a problem. Right? You're never going to have an array out of bounds problem, as long as your Q doesn't have more than max elements. Make sense? Questions? Is it all clear? Yes? Sorry, say that again. Mm-hmm. Right, so obviously this is not going to work. This is not going to work because eventually back is going to may reach max. And then you have a problem. So what do you do? How many of you know modular arithmetic? Mod? So you see how mod will save you? You just keep adding 1 modulo the maximum. Right? And what does mod do? So let's just say you keep doing this, and at some point your Q looks like this. This is 0. This is max. Let's say your Q is 4, 5, 6. This is front, and that is back. Now, if you want to insert another element, you could do the same thing, except you just do that thing percentage max. Right? So when back is equal to max, then maybe I need to make it max plus 1. Make it max plus 1. Yeah, so I'll do an example of this just to make sure that you guys get it. So, yes, back is an index. It's the same thing, right? The queue basically has two indices, front and back. It's just that those indices are moving in a circle. They're not moving in a line in the array. Yes? So let's do an example, and then I think it should hopefully be clear. Yes? So let's just say it's the last index. Yeah, I might be messing up my indices. So I'll do an example, and then I'll fix it. Yes? Yes, you will reach whatever is at 0. Maybe I'll take a 2-minute break while you digest this, and then I'll come back and then we can come back and do an example. So think about it for 2 minutes. All right, so let me work out an example of this. And yes, as people have pointed out, I've messed up my indices, and it should actually be, I'll write this all over again, but it should be max minus 1 and max if the array has size max. So let's just do this again. So the Q is maintained as an array of size, just to be clear, let me call it max size. So that is the size of the array, right? And so the last index is max size minus 1. But the way we're going to think about it, we're going to think about it as a circular array. So think of it like this. And so this is 0, 1, so on and so forth, until this will be max size minus 1. That's the index. And so now let's write our NQ and DQ operations, and then we'll walk through an example. So NQ int I. So we're going to think of there being a front and a back. So there is some front, and there's some index back. So you say back is equal to back plus 1 percentage max size, and Q of back is equal to I. So note that back will actually, so if your Q has stuff over here, back actually points or is the index of the last element or the most recent element that you added. And DQ basically does front is equal to front plus 1 percentage max size. Or you might want to say, I don't know, say int, first store the item, which is what is there in the front. Right, and I simply used item because I'm changing front, and so I just wanted to make sure I didn't mess up with that. Does this make sense? So let's actually go over what the percentage operator does. So remember, A percentage B in computer science, in math, this is called A mod B. This is the remainder of A divided by B. So this is the remainder function. Now we actually don't have to get too much into the guts of what A percentage B does. The only thing we need to understand is what happens in this setting. So note that I'm doing percentage max size. So let's actually use a simple example. And let's just say max size is 4. Is 4. So our Q can only have 4 elements, right? The index 0, 1, 2, and 3. And so let's just say max size is 4. And so if I'm looking at what the back index does, it does back equals back plus 1 percentage 4. So if back starts at 0, then what is back plus 1 percentage 4? So if back, let's say back is equal to 0 first. So what is back now? 1, right? Because 1 divided by 4, the remainder is 1. If back is 1, then what is back was 1 percentage 4? 2. And if back is 2, it goes to 3. Now what if back is equal to 3? And then you do back equals back plus 1 percentage 4. What is the value of back? 0. So it wraps around. Right? And that's all you need to know about the percentage function. So what it does is as you increment at the last index, it just moves it back to 0. Right? So this is really neat because all you do is just start with the original Q, which didn't have any percentages. You had this problem of, what's called rightward drift. And the fact that you can bump up at the end of the array, you stick a percentage max size, and then everything works out. So it's an extremely elegant solution. So let's look at a few examples to see what happens, just when max size is equal to 4. So typically what I do is front starts at 0. This is the initial. And this is, I'm going to write this down and then we can come back and talk about this. I'm actually going to start back at -1. And then we'll come back to this. There is a problem with detecting empty arrays. And so as is, there are certain situations where you'll have null pointer exceptions, but we'll come back to that. So let's just start with that initially. And so let's NQ42. Let's NQ97. NQ84. And let's do DQ and DQ. And let's look at the array sort of as this circular. Again, so the index here is 0, 1, 2, and 3. Right, so initially front is 0 and back is -1. So let's do an NQ. So when you do NQ, back is -1, -1 plus 1 is 0. So back is 0, and it says Q of the back is 1, which is what you want. So it puts 42 over here. And both front and back are indices to the same element. When you do NQ97, what happens? Yes? Yes, in the back? So back is going to move, and back goes here to 1. Then you NQ84. 84 goes there. Back moves here. Then you do DQ and DQ. So in a DQ operation, front just moves. That's the only thing that happens. And of course, it returns the item, but let's ignore that for now. What front does is it just keeps moving. So at the end of this, front is over here. So note that, of course, these don't change, but you don't have to delete them. You just don't access them. So now let's NQ 100 and NQE 5. So, well, 97 is still here. So you have front, 84. So when you NQ 100, 100 goes here, and back goes over here, and then you NQ 5. Back is at 3, so it loops around and goes back to 0, and it overwrites what's over here. So it becomes 5, and back points there. Does this make sense? So is 97 in the queue or not? No. 97 is not in the queue because it's only everything from front to back when you go clockwise, right? So this is the only thing that's in the queue right now. It's front to back clockwise. Front to back clockwise is the content of Q. Everything else, there may be something written there, but that's not part of the queue. That's just stuff that has been dequeued but not yet overwritten. Make sense? And so if you dequeue, then sort of front keeps moving in a circle. Does this make sense? So modular arithmetic is useful because again, like I cannot stress the simplicity and elegance of the solution. It's incredible, right? It's just one extra percentage sign over here, and suddenly this problem of memory drift goes away. There is one thing though, which is, so let's say we're at this stage, and let's do an NQ 40 and an NQ 9. Now I should have a problem because the queue has 3 elements right now. I added 2 more, so I exceed the size. So let's do this one first. What happens after NQing 40? This is where I'm going to answer this thing about what happens when you fill up the queue. 584, remember this is front. And so when you NQ 40, 40 goes here, and this is back. Right? So the queue, remember, is from front to back clockwise. At this point, what should happen when you do an NQ9? Yeah? There should only be one element in the queue, and that would be 9. What should happen? What should your code really do at this point? Somebody had basically the right answer, yeah? It should throw an error. Someone said crash, which yes, it should, but it's better if it throws an error. This should throw an error. So how does it know that it's actually filled things up? Yes? When front equals back, or rather when front equals back plus 1. Because back is wrapped all the way around. Yes? Back plus 1 modulo, yes. Modulo max size, yes. Henceforth, when I say plus for the rest of the 15 minutes, it's modulo. Yeah. So when front is equal to back plus 1 modulo max size, then it's possible that it's wrapped around. Yes?
Isn't it also possible that it's an empty queue?
It's also possible it's an empty queue, exactly. So both of these, so if you actually deleted everything, then front is also going to be back plus 1. So let's see that. So right now, front is equal to back plus 1 percentage. So when this condition holds, you actually know that what happens is either the queue is full or the queue is empty, which is somewhat annoying because it would be nice if this detected that the queue was full, then you could throw an error based on that. But it also can happen if the queue is empty. So let's just see that. At this stage, let's do 4 DQs. 4 times. So front is going to go there, 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 and then it's going to move back over there. Right? Each time you do a DQ, front moves by 1. So when front is actually ahead of back by just 1, the queue is either full or empty. And note that my initial condition had the same thing. Front is equal to back plus 1. So the queue is either full or empty. And unfortunately, just by checking, you're not sure which one. So typically, you need something more. Yes? So front and back are at the same position when the queue has size 1. Yes? When DQ is called, so when front is equal to back, there's one element in the queue. So you're allowed to call DQ. No, so let me just do this example. Let me just walk through this. I think this would be useful. So what happens when you do DQ 4 times? So it started here. Now to DQ, it has to remove 84. What that means is front is going to go there, right? And the queue is from 100 to 40. I do DQ again. Front moves to that. So the queue is 5 and 40. I do DQ again. So this is 1 DQ, 2, and then the third DQ, front is here. So the queue is just 40. At this point, I am allowed to do a DQ. I just cannot do 2 DQs. But how does the class remember what happened previously? Yeah? Right, so something has to remember that the queue is empty. So exactly, so what you need is either you have a Boolean like that or you can keep track of the size. Right? So what you need is a counter to track size or a Boolean flag to detect empty or need. This makes sense? There are other ways to sort of get around this, but sometimes you actually make the max size. You can keep a dummy element to sort of take care of this, but this is the most common solution. And keeping track of the size is really easy. Every time there's an NQ or DQ, you just increment or decrement. Yes? You could do that. Sometimes, although that might not be necessarily the case here, there's actually reasons to keep what has previously been deleted so that you can undo steps. And in that case, you might not want to set things to null. There are actually data structures that are called persistent, meaning that you can actually roll back part of your operations. And so in that sense, the fact that you store things and only move indices is helpful. But yes, you could do that as well. Yeah, hand in the back.
The problem with that would be that in a lot of languages, including Java, if you're storing a primitive type, then there is no null for
Yes. Yeah. Yeah. You can have various problems with that. So the counter is probably the quickest solution. It might even be better than the Boolean flag because the Boolean flag requires some amount of cleverness in the code, just to be careful. The counter is simple. You just NQ or DQ, and you just increment or decrement. So this is a common implementation of a queue. My guess is it might actually be under the hood in Java, although I'm not sure. But this is a nice example of modular arithmetic. And so what we've seen are two implementations of queues, or like almost three. One using linked lists, one using arrays, and fixing the problem in arrays using a circular array. Now, the last thing I want to say about queues is what is commonly used as a variant of queues called a priority queue. The way to think about priority queues, and I won't get into implementations of priority queues because that's actually part of 101, where there's a specific data structure called a heap, which is meant for this. But a priority queue basically says you insert something with a priority, and when you dequeue, you actually remove the element with the highest priority. So this is very common in maintaining jobs, or think of you have a series of jobs that are coming, and each job has a priority. And they all get into a queue. And when you want to process a job, you remove the job with the highest priority. Right? So think of objects. So maybe you might have a class job which has some int ID and int priority. And you want to maintain a queue of jobs such that you can insert jobs and you delete the job with the highest priority. Does that make sense? You insert jobs, you delete jobs with the highest priority. So in a standard queue, the priority is simply the time you inserted it. Right? So the oldest one that was inserted has the highest priority and gets removed. But in general, you could think of jobs having different priorities, and you maintain something called a priority queue, which handles these two operations. So any idea of how you would maintain a priority queue? Yeah?
Maybe have a linked list where you basically search it until you find a similar priority, or like whatever is less than whatever priority, and then insert your new thing right next to the thing in similar priority.
So essentially, you maintain a linked list where priorities are sorted, maybe in decreasing order, because then the head has the highest priority. So this can be implemented by a linked list with where the order is decreasing priority. Why decreasing and not increasing? Yes? Exactly. It's decreasing because the highest priority would be the head. And so if you instead wanted to delete the job with the lowest priority, you would make this increasing. So show you an example of that. Let me just think of my node having an ID, or let me put the ID here, and this is the priority. And this is, of course, my pointer to the next job. And so my priority here might be 5, 3, 1, and the job ID is, I don't know, some ID 1, ID 2, some ID 3, right? And the head points here. So to insert, you need to find the correct location. So to insert, say, a job with priority 2, so maybe, and this is some ID I'll just call foo, to insert this, that has to be inserted over here, right? So then once you insert this, you would have to modify the priority queue so that this points here, this points there. Make sense? That's how you would do the insert. Yes?
Do you find that a doubly linked list would work a lot better for something, especially as tricky as doing an insert in the middle of it?
You can actually, the problem with a doubly linked list is that doubles the number of pointers that you have to keep track of. Remember, it makes life easy, but it also makes life equally difficult for all the operations you have. It's probably worse. Because now you have to worry about the back pointer of the head, make sure that that thing is null. It probably will increase the complexity of your code. You can do it with a singly linked list. Because remember, when you insert, you start at the beginning and you kind of keep walking until you find the right location. Yes? Is priority queue basically insertion sort? That's a good question. So this is not, this is related to insertion sort, but you'll see that there are more efficient ways of maintaining priority queues. You can do it without doing insertion sort. The benefit of a linked list is you don't have to shift things around. That's why you would maintain it as a linked list. So if I asked you to write the code for insertion in a priority queue, do you think you'd be able to do that? Yes? That might be an assignment. Might be, depending on my mood. If I'm finally done with chess, I'll give you a, then I'll give that to you. Yes? I'm sorry, I can't hear. Sorry, can everyone quieten down a bit? I couldn't hear it. Yeah. Why not use a linked list for what? For all the data structures we've talked about? So this is called a priority queue. I mean, the name for the data structure, or rather the abstract data type that gives you these operations is called a priority queue. It's implemented as a linked list. So it's a distinction between, this is sort of the, think of it as almost like the spec of a data structure, of what you want, and this is called a priority queue. And a linked list is one way of implementing it. There are other ways of implementing it as well. Any questions about priority queues, stacks? So we'll be done with stacks and queues. I won't ask anything about queues in the midterm, but everything else goes.